That might help. Can you hear me? Can you hear me in the back? Okay. All right, so this is a lecture about fusion. It's not plasma physics. It's going to be probably the easiest lecture in the course, and I don't want to teach you too much about plasma physics. So it's more about fusion, which is a little different. I hope by the end of the lecture you'll get an idea for what we're here for. And we're not really here in this laboratory to make advances in plasma physics. We're here to make a fusion reactor. And this is basically our approach in the laboratory to make a fusion reactor. I know that you've had a lecture about ICF, inertial confinement fusion, right, in the beginning. So I'm steering away from that. So even though it says, can we make a fusion reactor, I'm largely going to talk about magnetic confinement fusion, not inertial fusion. So I want to cover how it'll work, what have we done, where are we going. Actually, before we start, let me understand where you're coming from. How many of you are physics majors? Most. Okay. How many are juniors? Seniors? Mostly seniors. How many going to go to graduate school in physics? Half. How many want to be plasma physicists or work in fusion? Okay. So I think this is about the right speed for you guys. Okay. Now I've been here 20 years at this lab. I've been in the field for 30 some odd years. I'll try to give you a bit of the history and the sort of stories behind the science, if I can, in addition to just telling you what the numbers are and so on. The first topic is how would it work? How does fusion in the laboratory work? How do we make fusion energy? And the goal is really to make energy, to replace oil and gas and other sources of energy, to make power plant, to make energy to power cities in the world. So I'll talk about where the energy comes from, what we need to do to get to the point where we make energy instead of use energy, which we're doing now. And then a bit about how to confine a plasma. This is the toughest part. How to confine a plasma long enough to make that energy. And then as an introduction here, just the conceptual design for a fusion reactor. And then I'll go deeper into a couple of these topics. What have we done and where are we going later? So fusion is easy. Fusion is a rather unremarkable process in the laboratory. People did it in the 30s with beams of deuterium. Fusion itself is really well known. We have no doubts the fusion process works. Fusion is, in this case, could be a deuterium atom and a tritium atom. Sorry, a deuterium nucleus and a tritium nucleus hitting together, overcoming the electrostatic potential between them, both positive charged. Tritium has 2 extra neutrons, deuterium has 1. And when you collide them together with enough energy to overcome that electrostatic barrier, they touch. Nuclear reactions basically need to touch the nucleus together with the other one to make a reaction. When they touch, they fuse and temporarily make this compound nucleus. And then it decays quickly into, in this case for D&T, which is the main fusion fuel we're going to use, a neutron with 14 MeV and a helium nucleus, which is an alpha particle at 3.5 MeV. So this is what you put in, D&T. This is what you get out, helium and neutron, most of the energy being in the neutron. So here's how we can make energy. You need to put enough energy into the fuel ions to start, to get them to collide. And the way we do it is not with a beam of deuterium hitting a target of tritium. That actually turns out to be not possible because you lose too much energy in other processes. But we make the whole plasma hot. Thermonuclear means hot nuclear reactions from thermal plasma. Of course, it's plasma above 1 eV. But in this case, you need to get it to 20,000 electron volts to make the reaction significantly big in order to make power. And the expression of that reaction rate is here. This is reaction rate coefficient, the number of reactions per cubic. This is the reaction rate in some units. And this is the temperature. The point being that below 10 to the 7th degrees Kelvin, you get nothing much. And you need to get it up to 10 to the 8th, 10 to the 9th degrees Kelvin. You know what the conversion between degrees, that's an annoying habit I have to ask questions. I know you don't like that, but how many degrees Kelvin is 1 EV? Degrees centigrade also. 1 EV, what is that in degrees centigrade? Right? 10,000. So 10,000 EV, which is close to the temperature you need, is 10 to the 8th degree centigrade up here. So why can't we get reactions down here at very cold temperatures? Can we make fusion at room temperatures? Yes, somebody said yes. That's good. How do we do that? You're just nodding your head.
Well, you can collide them in a linear accelerator.
Okay, that's cheating. Yes, you're right. But would it be possible to make fusion in a glass of water here? Yeah, you've heard about cold fusion. Maybe it's even before you were born. I can't remember now. It's about 15 years ago. People thought that you could actually make fusion reactions in water. And using a special palladium metal to somehow squeeze the hydrogen atoms or deuterium atoms together in the lattice of the metal. Squeeze them enough together to fuse. And some people bought that. In fact, some distinguished physicists thought it was possible. It's hard to prove something's impossible in physics. And there's always some people out there who are trying to make anything possible. So at some point, people thought cold fusion was possible. Basically, it was a mistake. As far as I know, as far as anybody knows, it doesn't really work. It's an experimental mistake. Yeah? Bubble fusion is realer. Okay. But it's realer because in those little bubbles that you get from compressing a sound wave and making a tiny little bubble, you actually heat the gas in the bubble. You actually heat it so that it glows. That's the sonoluminescence you get out. So it's again, thermonuclear fusion, but its temperature is still very low, only about 1 EV or a few EV. So it's not enough to make a significant amount of fusion as far as I know. So you need hot gases, hot temperatures to make fusion. You don't need the electrons. The electrons don't matter. You just need to combine the nuclei to stick together. But the electrons are around because you can't get rid of them. So it's a neutral plasma environment in which this happens. And the trick is you have to heat the plasma up. So you put in 20 kilovolts for the deuterium and 20 kilovolts for the tritium to get it started. So you put in 40 kilovolts. And what do you get out? For each reaction, you get out 14 MeV in the neutron and 3.5 in the alpha particle. So you have a gain possibly of 400 or so. And that's why we can make energy. You have a potential gain from the basic physics of the reaction of 400. So everybody knows and accepts the fact it's in principle possible to make a fusion reactor. All you need to do is heat the gas efficiently, not lose a lot of energy and other things you don't want to do, and collect that neutron, basically. The neutron is the thing that provides the energy to the outside world. Okay, so where do you get deuterium and tritium? Deuterium is easy. You can buy bottles of deuterium for almost nothing. We do it every day. On our experiments, we have bottles, gas bottles, not liquid, but gas, deuterium gas bottles. It's in water, any kind of water, seawater. 1 atom out of 7,000 is there. That's there. It's heavy water, it's called also. Heavy, meaning 1 atom of deuterium. Negligible cost. Where did that deuterium come from? Where did the deuterium come from? That's in the water. That's a good guess. Anybody else have an idea? Well, there are really 3 possibilities in cosmology, you might say. One is fusion in the stars, normal fusion reactions. But as you probably know, the fusion reactions in the stars do use deuterium, but they get deuterium from fusing hydrogen. So hydrogen is mostly what's in the stars. They make deuterium. Another way is when the star explodes, supernova, you can make a whole lot of mess, all kinds of heavy elements. The third way is the Big Bang, and that's my understanding that deuterium was there since the first few seconds of the universe. It just got created there at the universe's beginning. Heavy nuclei above iron got created in supernova, and intermediate stuff in stars. So the deuterium is there. It costs nothing to get out. Tritium is, so if you It's a little bit out of sequence here. If you can get the tritium, which I'll tell you in a minute, the energy in the deuterium in a gallon of water that you would get out by burning it in a fusion reactor is 300 gallons of gasoline's worth. In other words, take a gallon of water, take out the tiny little bit that's deuterium, which is easy. You just distill it. That's why it's cheap. Take the deuterium, put it in your fusion reactor. You need tritium, but I'll get to that in a minute. And you burn it, you can get out equivalent to 300 gallons of gasoline from that 1 gallon worth of deuterium. So it's potentially a great source of energy and universally available. I'm giving you this story has its ups and downs, and that's the upside. That's the motivation for it all. We have available in the Earth unlimited amount of energy from deuterium fusion, deuterium-tritium fusion. Okay, the first problem is where to get the tritium. Tritium is not so easily found. Tritium is, in fact, a radioactive nucleus, and tritium decays in 13 years. So you will not find any tritium on the Earth. 0. It's gone if it was there in the Big Bang. But you can make tritium, and it's kind of interesting the way you can make it. You can make it from the neutrons in your fusion reactor. So if you have a fusion reactor started, it doesn't tell you how to start it, but if you have one started, you can use the neutrons that come out. Of course, neutrons go through the plasma very easily. They're very high energy neutral particles. They hit the wall, and you put lithium isotopes in the wall, easy to find, lots of lithium around. When you hit a neutron into it, it actually makes tritium. And it turns out, just coincidentally, you can marginally make one tritium nucleus for each neutron, 1 plus epsilon. So in principle, I'm exaggerating a little bit. It's not that, epsilon is not 0.01. There's actually, you can make two tritiums or something like that per neutron, but not all the neutrons have this reaction. So in net result of all the possible configurations of a magnetic fusion reactor, you can just barely make enough tritium out of the neutrons that come out and make the energy for the fusion reactor at the same time. So you can make inside the reactor nuclear breeding of tritium from the neutrons that come out spontaneously from fusion and from putting lithium in the shell. So coincidentally, it's nothing more than that. We can have a self-sustaining fusion reaction where you put deuterium in, you make tritium in the vessel or near the vessel, you extract the tritium from the lithium, it's easy, put it back in and mix it with deuterium. 50-50 is the best reaction balance. And you keep going. Now, where do you get the tritium to start? We did tritium in experiments here about 10 years ago. You know where the tritium came from? Not a fusion reactor. Yes? Right. Yeah, exactly. It came from fission reactors. Some fission reactors make a lot of tritium they don't even want. In fact, heavy water, the Canada reactors in Canada, they're water moderated. They make a lot of tritium. They store it. They don't know what to do with it. So we just got some of it. So you can start it up with sort of using the tritium a nuclear fission reactor makes anyway. So that's not a problem. So what happens to this reactor? Let's say you want to make 1,000 megawatts. This is a big power plant. You know how much a house uses? How many megawatts does a house use, just to scale this? I'm going slow, but I'll be done in an hour. I won't go past 12. How many megawatts, or I'll give you a hint, kilowatts, does a typical house use? Just to get a scale for a 1,000 megawatt reactor, what we're trying to do. Huh? 10 what? Right, exactly. So a house uses 10 kilowatts. That's, if you look at your electrical circuits, you can 100 volts and 100 amps. You get a 100 amp service for your house, typically. And so how many houses can a 1,000 megawatt fusion plant run? 100,000. So it's a city, a small city. So what we're trying to do is power a small city with one fusion power plant. And what you get out is alpha particles, but they thermalize, they slow down, they actually heat the plasma. You need them to heat the plasma as they go from 3.5 MeV at their birth to thermal, and then hit the wall. And what do you get after they hit the wall? You get an alpha particle with electrons, which is a helium atom. So you can fill up helium balloons with it. It's perfectly harmless. So this is the bright side, part 2. Okay, so then what do you have to do? Sounds great. Well, here's where it starts to get a little sticky. The first thing you have to do is ignite it, like any kind of fuel, like you burn wood. What do you do to burn wood? You take a match, you stick it in the corner of the wood, and you ignite it. You don't keep blasting it with heat, right? You want it to spontaneously and continuously burn. Burning means self-generation of more heat from the heat. So the heat from the initial reaction is enough to continuously burn the rest of the fuel. You don't have to keep heating it. That's called ignition here. And ignition, anything else. You ignite a fuse for a stick of dynamite, and it's enough to ignite it. So ignition in DT plasmas means you don't want to have to put more heat in when you get this started. You want the heat of the alpha particle. Again, a coincidence. The alpha particle, as a product of the DT reaction, can heat the plasma because it's confined. You heard about confinement a little bit, maybe. The alpha particle is charged. It'll stay where it was born, pretty much. It has 3.5 MeV, whereas the plasma temperature is what that you need? 20 kilovolts. So it has 100 times more energy than the plasma. So as it slows down, it heats the plasma. So the alpha particle is the heating mechanism for a fusion reactor. It's part of the reaction. So neutrons go straight through the plasma and heat the blanket. I'll get to that later, and that's how you get the energy out. So ignition depends on alpha heating equals plasma energy loss. Maybe you went through this before with the ICF guy. So alpha heating rate is the rate of production of the alpha particles in terms of watts per cubic centimeter or watts or something like that. And the plasma energy loss is the tricky part. That's the energy leaking out of the plasma, which you have to replace by the alpha heating. Otherwise, it's going to cool off. So you have to have a balance in a fusion reactor at ignition between alpha heating and loss. And loss can be a lot of different things. I'll get into that later. Here, the alpha heating rate is described by n squared t squared. Why is it n squared t squared? Why is it n squared? N is the density of tritium or deuterium. Where does the n come from in the reaction rate? N squared come from? Why is it n squared and not n cubed or n? It's a two-body collision. And the optimum reaction rate is when it's 50-50. At 75-25, it's a little bit less. So that's where the n squared comes from. There's a constant depending on the D and T physics. And there's a t squared. Where does the t squared come from? Temperature squared in the reaction rate. If you were quick, you would have seen that a little bit earlier. Whoops. In this reaction rate versus temperature. In this range, you actually don't want to be up here. We want to be down here. It's hard to heat the plasma. You'd like to be at lower temperature as possible. Kind of looks like it goes like t squared. Does anybody know why? Why not t cubed or t to the fourth or? I'm glad there are no answers because there is no good answer. It's nuclear physics. It's nuclear physics. Nuclear physics is not well understood. It's just the physics of how these two atoms stick together. And it's some function of their mutual energy. And it's really complicated, if at all possible, to derive that. It's no simple physics. It's just the approximation to the reaction rate near the temperatures of interest. So some constant times n squared t squared equals this loss rate. Now, this is not much physics. This is the energy stored, 3/2 NKTE plus TI. So it's 3N, where N is any and Ni are equal. T, that's the stored energy in the plasma. And this is some loss rate. And this is where most of the trouble lies. We're not telling you what the loss rate is, but we're just describing the loss rate in a single parameter, tau E, the energy confinement time or the energy loss time. If the energy was lost in a microsecond, and we know we had to have a certain amount of energy in there, the heating power would have to be tremendous. The alpha heating power would be too much. We'd like to keep the energy in from leaking out, keep the energy in as well as possible. We don't want the energy in the plasma to leak out. We want it to be heated by the alpha particles and stay in there until it ignites. We don't want it to leak out. And the way it leaks out is particles and heat hit the wall, and radiation comes out. There's a lot of mechanisms. So if you divide by NT, you get NT tau. Can you see that? That's the conventional condition for an ignition. NT tau equals some number, and these are constants. And there are two limits which are interesting. So this is the ignition condition in terms of density, temperature, and confinement time in seconds. For MFE, you want to typically have 10 to the 14th per cubic centimeter, 20 kilovolts, and turns out you need 5 seconds. 5 seconds, the energy has to stay in there, and typically before it leaks out, to make ignition in a magnetic fusion reactor. In inertial fusion, it's quite different density, 10 to the 24th, same temperature because the cross-section is the same, and 0.5 nanoseconds. So you trade off density and time here. But they both methods have to meet the ignition condition in order to make fusion energy. So I think that's the only equation I have in this lecture. So you want the plasma heat to stay in. Our way of talking about that is you want the plasma energy to be confined. You don't want it to leak out. So how do you confine plasmas? This is dark, dark, dark. Maybe I'll make it darker. That was a good thing. That's too dark. You're all going to fall asleep. But that's okay. I don't know how to... Is this bothering to some of you, or you rather have dark? As usual, the most, like, one person answers for the whole group. Who is it? You're already asleep. Okay. I wanted to see the picture. The sun is a fusion reactor. Gravitation confines it. So the fusion reactions go on in the very core. At the surface, it's quite cold. Not enough to make fusion. Do you know how hot the surface of the sun is? How much? 10,000 degrees Kelvin. How many EV is that? EV. One, right, 1 EV. You need 20 kilovolts for making fusion. So there's no fusion on the surface of the sun. It's quite cold. In fact, it's not much hotter than a tungsten light bulb filament. This is a picture of a solar coronal loop. But the point is actually that the reason it's doing this, it's because magnetic fields are guiding the plasma around this loop. So it gives you a hint how to confine plasma in the laboratory with magnetic fields. Gravity is too weak. And you know what this is? Inertial confinement. I'm interested to know whether your lecture on inertial confinement mentioned hydrogen bombs at all. Okay, you know, that's huh? Yeah. Well, I'm going to tell you, if they didn't, that inertial confinement fusion works, and it has been demonstrated. It actually is hydrogen bomb. Hydrogen bomb is a nuclear fission bomb, a small bomb, fission bomb like the Los Alamos bomb, surrounded by deuterium and lithium. Okay, so it's using exactly the same reaction I just talked about. No tritium, just lithium and deuterium, and it makes a huge bomb. And it works by inertial confinement, squeezing the fuel in to a core and then having it blow up. So what they're trying to do at Livermore, although they may not like to say it, is making a little bomb. I won't talk about that anymore. Magnetic confinement. This is a picture of our, actually it's not our machine, but ours looks very similar. Did you see NSTX yet? Okay, this is what NSTX looks like when it's running, very similar. Makes a ball of plasma, and this sharp boundary is actually not the wall. This sharp boundary is the magnetic boundary that confines the plasma. There's a magnetic field that's guiding it around here. You can see the field line spiraling here. This is the direction of the field. And when the magnetic field line closes on itself, which is not impossible, it's actually possible to close a magnetic field line in three-dimensional space, you get what's called a flux surface, and you can stick particles to that. You know, I suppose you've seen already that if you have a magnetic field, the electrons and ions circulate around it. This must have been touched on earlier. The gyro radius is the characteristic distance it can move away from the magnetic field, and the gyro radius depends on the velocity. And given the velocities of ions at 20 kilovolts, that gyro radius is typically a centimeter in a pretty strong field, like 20 kilogauss field. So here's an upside. Again, they're kind of climbing up the mountain or getting positive feeling for this maybe, and then I'm going to bring you down by the end of the talk. It should be easy to confine a plasma with magnetic fields. It should be really easy. And people, when the start of a magnetic fusion program, thought it was really easy. And they thought it was really easy because all you need to do is have a magnetic field of 20 kilogauss, which is pretty small, go in a loop, a circle. And then the ions will just follow the circle around and never leave. And if it never leaves, it's never going to lose, or very slowly lose energy. And it'll be confined. And you can do it with a very small field, and it's very easy. Electrons are even better confined because they're more massless. I'm going to skip about 15 years of fighting with magnetic confinement between 1951 and 65 or so, during which time people realized that it wasn't so easy. In fact, it was terrible. The magnetic confinement idea that you just saw just didn't work. There was all kinds of problems with it. And I'll get to why in a minute. But the solution was the Tokamak. And this is the best magnetic confinement system that exists right now. And this is the basis for our magnetic fusion reactor. Tokamak is a Russian acronym. Anybody speak Russian? I can't pronounce it in Russian, but it's an acronym for toroidal, which is donut-shaped, magnetic, which is because it has a magnetic field on it, chamber. So it's a toroidal magnetic chamber. Oh, I wrote that there, okay. And these small blue things are the thing that makes the magnetic field. Remember I told you if it goes in a circle, it should be fine. If the magnetic field line just goes around in a circle, which is what you get when you make the coils like this, it should be great. If you just do that alone, it's going to leak terribly because of gravity and curvature drifts, and I won't discuss those. But if you give it a little twist, if you give the magnetic field a little twist, what happens is it's a very little twist. You can see that field line there, very little twist. And that twist comes from a current that you induce in the plasma. You make the current go around this way, and like any current, it makes a magnetic field by itself. And that magnetic field is in this short direction around. So the magnetic field, steady magnetic field from these coils, plus the field from the internal current, makes a twisted helical magnetic field, which solves the problem, essentially, of the first approximation, magnetic confinement, that was not solved previous to the Tokamak. You need that twist. Basically, you take the top of the machine and you bring it to the bottom. You take the plasma at the top, you bring it to the bottom, the plasma at the bottom, you bring it to the top. So if ions want to drift up, they get confused. They want to go up at the top, they want to go out. But then they get moved to the bottom and they want to go up, but they go in, okay? So wanting to go up is the property of the drifts. So if they want to go up at the top, they start to get lost, but then they're brought around by the field to the bottom, and going up at the bottom means going in, so they go nowhere. So that's the Tokamak. And you make the current by this transformer in the center. It's just like a primary of a transformer that has the secondary, the plasma itself. And of course, the plasma is conducting. So this is the end of the introduction, but it's the most important part. This is what a fusion reactor based on a Tokamak would look like. Everything outside this red blob there is conventional power plant. You take the heat out, you boil water, you move you first take the heat out with a working fluid that circulates, then you boil water, and you put make water into steam, and you turn a turbine, and you make electricity. Everything is conventional. It's just the source of heat that's different. And the plasma core here is the Tokamak, and that makes heat through the neutrons. The neutrons go out of the plasma, they hit the wall, they're absorbed in the wall. Do you know how, let's say you have iron, do you know how far a neutron will penetrate an iron? Let's say you wanted to make an iron Tokamak reactor, and you wanted to build a wall around it to stop the neutrons. And that's good. You actually want to stop the neutrons to extract their energy. How thick would that wall have to be? There's no reason you should know this. 14 MeV. Huh? Meters. That's well, actually, it's interesting. That's the answer, but for the wrong reason. The actual stopping distance of a neutron in a piece of iron is quite short, only 10 centimeters. but some get farther out, some go farther. And so the blanket, the actual structure that stops the neutrons, converts the energy of the neutrons to, or gives the heat to the water or the circulating fluid, and has lithium in it to breed tritium. All of that is typically a meter thick. So even though you could stop the neutrons, in most of them anyway, in 10 centimeters, you have typically a meter thick extraction of energy from the neutrons. Yeah?
Where is this blanket from?
Just outside the plasma.
Before the wall?
Just outside the wall. I think I'll show a better picture of it. So you need a vacuum chamber to make the plasma. Plasma density, I should have touched on this point. Anybody remember what the plasma density is typically in a tokamak? From what? Huh? 10 to the 13th or 14th per cubic centimeter. How big is that compared to the density of air? What's the density of solids? Good. What's the density of air? Nothing, right? 10 to the 20, 10 to the 19th atoms per cubic centimeter. So the density of the plasma we're looking for is 10 to the 14th. So it's about 1 million times less dense than air. So to get to that density, you don't want air around. You pump out a big vacuum chamber first. And that's basically a vessel of iron or steel, not 10 centimeters thick, as thin as possible. Big vacuum chamber. Outside of that, you put your blanket to slow down the neutrons and breed tritium and convert the energy to hot water. Yeah? No. No, I'll get to that at the end. That's one of the problems. But it's nuclear engineering. It's fairly straightforward. Calculations can be done based on neutron cross-sections for different materials. By fairly straightforward, I'm not saying it's doable. I'm saying conceptually it's doable. Okay, so now that's the introduction. I'll tell you what happened in the last 50 years. Everything that I said so far was known 50 years ago. And people were very optimistic because the hydrogen bomb project only took a few years, from 45, 46 to 52. And people made a fusion bomb pretty easily. They knew the cross-sections. They had an atom bomb, which helped. And so there was a tremendous amount of optimism. This lab was founded in 51, just about the time in fact, it's connected. This lab was started by people who were connected to the fusion bomb program and wanted to make the same energy available for useful purposes. That's 50 years ago. What happened? I'll try to give you an overview and then tell you some details about the problems. And then the last part is about where are we going. So that, in a nutshell, is where we've been in 50 years, or what happened in 50 years. This is the first fusion machine at Princeton. It's actually smaller than the one outside in the hall. This is Lyman Spitzer, who founded the lab, professor at Princeton, and actually an astrophysicist. He was also called the father of the Hubble Space Telescope. He had the vision to make a space telescope in I guess it was the 60s. Also started a fusion program here. That was the first Stellarator. Mike will tell you about Stellarators next. I won't say much. It's kind of like a Tokamak. And this is Jet, the biggest Tokamak in the world. And that's typical European man in a bunny suit. You keep the suit on because you don't want your hair and stuff like that to get on the machine. You just dress cleanly. This is big. This is a big thing. It's much bigger than the height of this auditorium. It's basically $1 billion machine. Started out with, so here's the thing. You can make 10 to the 13th plasma really easily. No problem. A high school student can do it. You can make a 10 EV plasma pretty easily. You know, a fluorescent bulb is 1 EV. So part of the problem was the temperature. It's hard to make a 10 kilovolt plasma. It's easy to make the density you need. They knew the conditions they needed. The confinement time was really lousy. It was like nothing. So they made a plasma in here and it leaked out almost immediately, almost as fast as the ions could carry it to the wall. So the confinement problem and the heating problem were what we've struggled with for 50 years. And by this time, this is getting to the end of the story, we have 10 to the 14th, no problem. 20 kilovolts now is no problem. We can get 20 kilovolt plasma anywhere. Anybody in the world with enough resources can do that. Japanese did it. Koreans can do it. Chinese, Indians, anybody who has a lab and a couple of $1 million, maybe $50 million, can make a 20 kilovolt plasma. It's easy now. We have heating systems to do that, and we know enough about confinement to do it. But our energy confinement time is still the limit. Now, that's the problem we're struggling with. We can't keep the plasma confined for the 5 seconds we need to make a fusion reactor, even in a machine this size. Of course, the bigger you make it, the better the confinement. It's like putting insulation on your house. The more insulation you put on your house, the thicker you make it, the better heat is confined. So we want to make the magnetic field, which fills this thing up entirely, the magnetic field bigger. And where we're going is to make the next step bigger to get to the fusion reactor. But let me now fill in some details about the Tokamak history. And I think you probably can't see this, so I'm not going to emphasize it. But this is a historical plot of this parameter NT tau. I told you about the ignition condition. This is actually values from machines. And this is the temperature. So you need 20 kilovolts. Let's just stick around here. This is the history from 65 to 2000, going up sort of vertically. Vertically means good. Vertically is good. You want to be up here at ignition, which is about a certain number times 10 to the 20th in these units. You want to be at about 20 kilovolts, which is about here. And we started here in the Russian machine in 65, and then went US machine here right at Princeton, French machine, Russian machine, French machine, another Princeton machine, MIT machine, JET, D3D in San Diego, Italian machine, so on and so on. I started on Tokamak work when I was a graduate student in 74, right around here. So I've seen it go up, NT tau go up 3 orders of magnitude. So we made a lot of progress is what this tells us, but we're still far from ignition. Far meaning an order of magnitude, factor of 5. Here's another way to see that. This is the fusion power. This is the worst PR graph we have in the sense that it's the most misleading. I didn't make this, but this is the fusion power per pulse over time, and we started making that many watts or joules, nothing, out of fusion, and we're up to making 10 million watts. We did it in TFTR, 10 million watts of power for about a second out of fusion reactors. Doesn't mean we made ignition, we just made fusion power. And this is supposed to tell you that it happened fast compared to the computer, Moore's law, computer chip law. But it's misleading because a lot of this was just, I think it's somewhat misleading. A lot of this was building bigger machines and spending more money and pushing hard on technology, not so much physics. Maybe that's true for this too, technology. And here's where we want to go up here in ITER, and I'll get back to ITER. It's the fusion ignition machine. Now, if you remember back a few slides ago, I told you I'd tell you details about 4 issues, and I'll just do one per view graph, I think. Confinement, pressure limits, how to get a steady state plasma, and plasma wall interactions. And then I'll tell you about where we're going. Whoops. Okay. Confinement, as I told you, is the most difficult thing. How well is the plasma heat confined in the magnetic field? And there are 2 approaches to understand this. Well, let me say there's an interesting split in the community. Half of the community wants to understand it. And the other half says, we're never going to understand it. Let's just build a bigger machine. Okay, and so far, the bigger machine guys have always won. Okay, the history of magnetic fusion is building a bigger machine. And this is a plot of basically confinement time from 10 milliseconds up to a second here. And these are bigger machines, sort of like 60s, 70s, 80s, 90s. And one approach is to plot it on log-log scale, this confinement time. And this is a mysterious parameter which I won't even begin to tell you about, involving the magnetic field strength, the amount of current you put in, the amount of heating power you put on, the density, all kinds of empirical parameters, like an engineering analysis you do by wind tunnels. You kind of do a purely empirical, that is no physics, regression analysis of the data, and you find what straight line fits the data best. You extrapolate up to where you want to be at 5 seconds, and it tells you what you have to do without really understanding it. So that actually was the way we designed ITER, the machine that is the next step and will be close to a fusion reactor. In parallel, half the community, and I count myself among them, think this is stupid. And especially when you reach the point where the machine's going to cost $5 billion, you're asking for trouble because there's no justifiable basis in terms of physics to make that extrapolation. So you want to understand what we have so far, and that's done by theoretical calculations, theory. And here's an example, an extreme example of a fit between experimental measurements of this is stored energy, but it's like confinement time, and theoretical predictions. In one narrow case, one group of guys doing very sophisticated calculations on a computer were able to predict the trend pretty well. And they don't claim better than 20% or so. Most people think that's highly optimistic. So confinement is a problem that we don't understand the solution of. We don't understand it. We do know that building a bigger machine will help.
On the basis of the graph on the left, should we conclude that we'll have a practical fusion reactor for 10 years?
Well, you tell me after this is over. I think that within 10 years, no, that's for sure. So here's an example of how we're trying to understand this. And this is just for, I hope these things go. These are movies. This is a simulation. You know, the reason it's difficult is these are nonlinear equations, just like this guy was telling you. Nonlinear equations, only in extremely simple cases can you solve them analytically. These are extremely complicated equations with 20 or 50 terms. So you throw everything on the computer, you get the biggest computer and the fastest computer in the world, and you do a numerical simulation, and you get a result. And this is the state of the art. This is... there you go. That's a piece of the Tokamak. That's the small part around. The other side is over here. This is the smallest cross section. This is the turbulence in the Tokamak. In case you didn't realize it by now, the reason we have anomalous energy confinement, energy loss, is that the plasma is turbulent. You know what turbulence means? Turbulence means we don't understand it, but it means fluctuations, small-scale fluctuations. So what you thought was a quiet plasma is broken up into these little cells, like little vortices, or little things that you see in the pot of water. You see not bubbles, but you see convective cells, little cells carrying the energy and particles up from the hot part to the cold part. Well, in a pot of water, it's 100 degrees C at the bottom, and it's maybe 60 degrees C at the top. So 40 degrees C is enough to make tremendous convection, which is small-scale random fluctuations in velocity in the case of water, and it carries the heat up. Here's a 400 million, 200 million degrees temperature difference in 1 meter or 2 meters. Tremendous source of energy, free energy, temperature gradient that could make turbulence, and this is what they calculated to be. And basically what happens is each of these little bubbles of, not bubbles in the sense of absence of plasma, but little highs and lows of density randomly walk out. Just take little steps, one hits the other, and they randomly leave, and little steps, little steps, little steps, and the energy leaks out. This is a picture, actually I made it with some help, of turbulence at the edge of NSTX. I won't tell you much about it, but we actually have pictures of the turbulence. This is real turbulence in the plasma. 10 microseconds, this happens very fast. The turbulence time scale is microseconds, and the space scale is centimeters. So what we're dealing with is a plasma that's very big, but it's broken up into tiny little bits of fluctuating stuff. Sometimes it gets better, like this is a good confinement plasma. It looks almost fixed, right? Sometimes it is kind of fixed. And sometimes it has waves like this and shoots out little blobs of stuff. That's towards the outer wall. It's got shot out. It got shot out, actually, the speed of this is like a rifle bullet. It's really sped up a lot. So we have calculations, we have measurements, but have we got them together to the point where we understand it? No. So that's a big problem in magnetic fusion. We don't understand confinement. Enough said about that. Then the other problem, a separate problem, is about plasma pressure. Now, I haven't touched on this. I think somebody will, about MHD instabilities. What we call MHD instabilities are pressure limits. If you have a plasma in a magnetic field, the magnetic field can, you might say, confine the plasma by magnetic pressure. The magnetic field has a pressure. You can imagine the magnetic field pushes on the plasma. It's not the single particle picture, it's a fluid picture. I think it's how much pressure does a 4 kilogauss magnetic field exert? Okay, how much pressure could a 4 kilogauss field exert? And how big is that compared to the plasma pressure we need for ignition? That's the question we're trying to answer. Turns out, to get to this ignition condition, N 10 to the 14th, T 20 kilovolts, NT is a pressure. It's actually a pressure. It's about 10 atmospheres. So in the center of a magnetic fusion reactor, we have to get to the ignition condition, 10 atmospheres worth of plasma pressure. And we have to have the magnetic pressure essentially pushing it in from all sides with a force or a pressure bigger than 10 atmospheres. And it turns out, if I'm remembering correctly, 4 kilogauss is 10 atmospheres of pressure. So you really only need a few kilogauss pressure in principle to confine the plasma. But it turns out that before you get to that point where the plasma balances the magnetic field pressure completely, before that point the plasma becomes unstable, becomes kinking, and it sort of wobbles and gets very unstable. It's kind of like a top that's slowing down. It just kind of wobbles and wobbles and wobbles and disrupts. It actually pops like a balloon. I won't go into detail, but that pressure limit is a separate problem from the confinement limit, even if you have good confinement. In fact, in TFTR, we had really good confinement at the end of the machine, and our problem was this pressure limit. It wasn't the confinement in TFTR, limiting our fusion power. And this is solved by not turbulence equations and turbulence simulations, but it's called MHD simulations, lower frequency coherent modes that represent the wobbling. Here's a picture. I don't have a movie of this, but some nice animations of what happens, some nice simulations. Here's a picture of some of the wobbling. And what happens is the plasma pressure, a beta, goes up and up and up and up. And at this point, something happens. You keep the power on. At this point, it goes down for no apparent reason, but the reason is it starts to wobble and leak. So pressure limits are another problem, number 2 problem. Current drive is a number 3 problem. Maybe you remember that I told you that a Tokamak has current in it and it comes from a transformer. The property of a transformer is it can only go so far. You get a transformer by making dB/dt, right? E is dB/dt. So you make a change in the magnetic flux through a loop, and that creates an electric field, and the electric field creates the current. But how can you keep increasing the magnetic flux up and up and up? You can't do it. You reach a limit to the field you can make. So a transformer is only a certain number of volt seconds or a certain number of current times time. And after that, your transformer fails, basically. And we've reached that limit almost every machine. We designed the transformer in the center to be as big as possible, but it cannot keep making current. And that's the flaw. The biggest flaw of Tokamak is that it cannot continue to make current in this way it started up. It has to have current drive. And this is extremely difficult. This is an art form, a science, an engineering challenge, and a physics problem that's difficult, okay? But you can do it. People have struggled with this for 20 or 30 years. Nat Fish is one of the innovators in this field. How do you make a current without a transformer? Probably tells you the answer. Basically, the 2 ways. One is to shoot beams in. You actually shoot atomic beams in, and they bounce off the plasma electrons, and you can actually drag the electrons around. That's expensive. The other way is with radio waves. You can actually make a current in the plasma with radio waves. And they actually drag electrons around. If you make your radio waves go in one direction, the direction you want the electrons to go and the current to go, you can actually drag electrons with a radio wave. And this is a radio wave launcher on NSTX. You can actually launch waves and drive current. Again, not terribly efficiently, but it's been done. And in fact, it's been done for 2 hours in a little Tokamak. You can actually do it. The question is, how efficient is it? And it's marginal in that respect. So that's the 3rd problem of Tokamaks. Stellarators, here's a picture of a giant stellarator in Japan. Here's a Japanese man. This is a superconducting stellarator. Stellarator is the name Lyman Spitzer gave to his version of the magnetic confinement system that I showed you earlier on with his this little table. It gets the twist I told you about, not from a current running in there, but twisting the coils. So it's actually got twisted coils. You can see some of them here. Looks like a science fiction movie, but actually it's like 2 meters or a meter with a plasma in it. It's a giant stellarator, and we're building one here too. I'll show you in a minute. That's one solution to the current drive problem. Forget Tokamak, just build a stellarator. I won't say much about this. The fourth problem, and also each of these problems is potentially fatal. Okay, I won't try to kid you. Any one of these can fail. And if it fails, you will never make a fusion reactor this way. So we have to juggle these 4 balls and many others as well to try to make a fusion reactor out of magnetic fusion. Here, the problem is the heat is leaking out. It's got to leak out. You can't just put heat in and store it up forever. It's got to leak out. It leaks out in 5 seconds. Where does it go? Well, it's really hot gas. It's like a blowtorch, you know. It's hotter than a blowtorch. So when that heat gets to the wall, it tends to vaporize anything. So you stick your finger in there, it's going to be gone. Okay, you stick a piece of iron in there, it's going to melt. You stick a piece of carbon fiber composite in there, and maybe it won't melt. And that's what this stuff is, carbon fiber composite, very strong. It'll vaporize a little bit, but it won't melt. And you try to spread the heat over a large area to keep the local evaporation down. And this may or may not work. People are struggling with solutions. One solution for the future is actually weird. What we're doing, you probably saw it on CDXU talking about lithium. To flow lithium, stream of lithium, liquid lithium down the wall, like down here, and take the heat out right at the surface of the wall with lithium liquid flowing through the edge of the tokamak and out to carry the heat away. Okay, 25 minutes or less, then where we're going. So I told you what we're trying to do, where we've been, and now where we're going. This is sort of a, our field and our work at the laboratory is a mixture of experiment, theory, simulation, and politics, okay? And this is the political side, you might say. Politics comes in because we need to spend a lot of money, and we need to produce a useful product to justify that money. And here's our vision, our leader's vision for the future of where we're going. This is introduction to actual plans for the future. In the widest sense, in the largest view, most global view, you want to start making electricity about 2050. Start making fusion reactors. Make one by 2050. That's pretty close to our goal. Some people say 2040, 2035. I think it's pushing it. But 2050 is the assumption here. Once we make one working fusion reactor in the world, and it will be a world project, then we assume that it can be duplicated and it can grow 1 or 2% a year by building copies of the plant. Basically, it would be the same plant everywhere. You don't want to mess with it once you've got a design. And then by 50 years from then, you'd make enough energy to supply half the world's needs or some good fraction of it. So that's where we're headed. How do we get there to that first reactor? That's the problem. How do we get here to make one even? This is a conceptual drawing of kind of our strategy. Strategy, in this case, has 2 axes. Advance in large-scale fusion engineering technology. In other words, pushing on the technology with what we know today. And this axis is innovation, understanding the science, and making a better mousetrap, making a better magnetic confinement system. So one could take either extreme position, say, let's just forget about the science and let's just build that bigger fusion reactor and heck, we'll see if it works. And the other extreme is saying, well, let's not spend $5 billion on what might not work. Let's try to first think of the best possible magnetic fusion reactor, try it on a small scale, try it on a medium scale, and then take the step for technology and pushing it to a reactor. And we wind up in between is where we wind up. This is a 3-pronged and maybe a 4-pronged strategy of our U.S. fusion program to have some innovation, and Mike Mel will talk about that after lunch, called alternative concepts or innovative concepts here. Basic science, they have some effort on basic plasma physics, as you've seen. It's important to understand that. Some advancement to the tokamak. This is a little bit more conservative. We say take a tokamak, but try to make it a little bit better. And we have actually 2 groups working on that at MIT and GA. And then there's a fourth prong, which is towards ITER. Did you hear about ITER yet? ITER? It's the International, I'll come to this again, Thermonuclear Experimental Reactor. So this is the next logical step after JET and TFTR to make towards a tokamak reactor. In this step, you don't really have to know much more. You just push the technology. Up until recently, we were kind of, well, the history of the fusion program sort of waffled back and forth between these things. Right now, we have a significant interest in ITER in this country, and we might well join up with ITER. This is it. ITER is a humongous machine. It's almost, for me, I started, in small tabletop things and saw TFTR is a big machine, the size of that jet machine. But this is mind-boggling to me. I worked on lots of Tokamaks, but where's our typical man? Oh, there's no man here. Well, then it's not so mind-boggling. It's a Tokamak. The man's about that size, this little blue thing. This is a giant version of jet, basically. It's 3 times the size. It's 6 meters major radius, and it's 2 times the size. 6 meters major radius in linear dimensions instead of jet is 3. So it's 8 times the volume. It's a humongous machine. It's like 100 feet high if you count everything. It's got a giant superconducting magnet. Got a transformer here. It's a pulsed machine. Doesn't have steady state capability. It's not a fusion reactor. It might get to ignition. It should get to ignition, but people are conservative. It'll make 0.5 gigawatt or so of fusion power. The record so far is 10 megawatts. Should have a pretty long pulse, long enough to see what goes on, but no electricity. This is still not a fusion reactor and could not be made into a fusion reactor. This will not make net electricity. You need more electricity to run this thing than you could ever get out of it. This is not often stated by the advocates of ITER, but it is true. This is not a prototype of a fusion reactor. It's the next step. That's why it's going to take so long, because this thing will take 10 years to build, 10 years to run at the minimum. And then you have to start again, one more step, and make your fusion reactor either smarter or bigger than that. Now here's another version of the ITER story. I mean, this is incredibly, and it's not the physics that's complicated, it's the technology and engineering is extremely difficult. Here's a person. This is actual mock-up of a TF coil. And this is it a sector? Yeah. That's a vacuum vessel sector. That's a piece of the vacuum vessel. A TF coil actually goes outside of that. And then the cryostat and the whole thing is bigger than that. So this is the size of a person. Plasma is that big, basically. It's not much more than taking jet and enlarging everything by a factor of 2. It's a little bit more, but basically it's a brute force approach, engineering, empirical scaling approach. And if you're lucky and it's approved, which it hasn't been, and the money is found, which it hasn't been, the international community, the Europeans, Russians, US, Chinese, Koreans, Japanese, will build it by 2015. So if you want to go into fusion research, you'll be dealing with this in 15 years if we're lucky. And as I said, that is not a fusion reactor, but this is. This is our design for a fusion reactor based on a tokamak. It looks, at first sight, the same thing. Okay, the man is here. The reactor's pretty big. It has a toroidal field coil. It has a transformer. It has everything that small tokamaks have. In this case, this is a design that was worked through. The engineering was worked through. The physics was worked through. It's based on making a lot of assumptions about the engineering and physics, though. But this put together is able to create electricity for a competitive rate. That's the bottom line. You want to be able to sell electricity for 5 cents a kilowatt hour. You pay 10 cents or something. 10 cents is probably okay. We have a target of making electricity at competitive rates, but we don't know what the rates will be in 50 years. They might be much higher, too, given that we may not have any more oil and gas or not want to burn it anymore. So our target for reactor, where we're going, is towards this. This is the best design called Ares for a Tokamak reactor that's ever been done. This is it. We have big books about it, but that's the picture of it. It's actually smaller than ITER. You might have noticed the man is bigger. So we're assuming that we're getting smarter to some degree and cheaper. It's cheaper than ITER. So if you want to make a reactor, you have to make more power. You have to build it cheaper. You have a long way to go from ITER to a reactor, but that's where we're headed. I'm just going to skip. There's some engineering issues here. They're innovative. I'm kind of running out of gas myself. Innovative concepts. Mike will talk about that. I'm almost done. Oh, this has that little, and then interesting. These are laboratory scale experiments. Basically new ideas that are being tested out. Here's a Stellarator that we're building here, hopefully in a few years. It looks like somebody really messed with that. And it's kind of bent out of shape, but that's actually a very, very, very carefully designed shape of the coils for the Stellarator to make a twist in the magnetic field. And we're starting to build that, actually. So here's something I wanted to say, and then there's one more view graph, I think. How can we do better? So sort of the lecture had two parts. The first part was, it's easy, we know how to do it, shouldn't be a problem. Second part was, well, wait a minute, it's hard to do this, it's hard to do that, it's hard to do this. And I wound up pretty negative, saying it'll take 50 years. And it's not clear it can be done at all in practice at an affordable, in other words, to make electricity at an affordable rate. What can we, this is trying to be inspirational to you young people. What could we do better? How could we make a conceptual breakthrough here? How can we fix this problem, which we got into? One way, and I think the best way is to figure out what is actually going on in the present machines. And I think that's possible. And I think it's possible because of our computational ability with supercomputers. Just now we're able to calculate turbulence. I showed you some of the movies. We still do not know how to relate that exactly to what we see, but given maybe 10 times or 100 times the computer power, and given 10 times or 100 times our ability to measure things like turbulence and find out exactly what's there, and then given some time to compare the experiment and theory carefully, we should be able to understand exactly what we have. There's no physics that's really unknown. It's not as if you're trying to find the top quark or a Higgs boson. It's Maxwell's equations, Newton's laws, materials, nuclear physics. Everything is known. It's just the turbulence and the MHD instabilities that are not known. And those can be dealt with through equations, fluid equations, kinetic equations that can be put on the computer and have been. If we can do that, then we can say we understand what we have. Let's see if we can design the next step on the computer. And therefore, we do not have to build ITER and see how it works. We should be at that point pretty confident that we know how to design the best possible fusion reactor. And maybe there is no solution. Maybe there is. And it's a solution that we haven't foreseen. So once we get to the point where we really understand things, we can let the computers run day and night for months and months and hopefully come up with a better solution. I don't know what it is. That's possible. And people are working on it. A lot of us are working on it. Technological innovations, well, this helps. If we can find a superconducting magnet, I didn't say why you needed a superconducting magnet. It's because you need to keep the magnetic field on for a long time, months and months, and it uses too much energy to drive it with copper magnets, so you want superconducting magnets. They have to be cryogenic now, very cold, and it takes a lot of technology, liquid helium and so on. Room temperature superconductors would be a great step forward, and they're, as far as I know, possible, not done yet. But a temperature limit of superconductivity is going up over time. And another problem I haven't talked about, I skipped it, was radiation resistance. This, I want to say this clearly if you haven't heard it before. The Tokamak is a nuclear device. Tokamak makes radioactive material. It doesn't use radioactive material as fuel. It uses deuterium, which is not radioactive, and tritium, which is, it is radioactive, but it's contained within the vessel. It's made inside. It makes a neutron, which is not, actually doesn't stick around. But where the radioactivity comes in is a neutron hits the wall and then transmutes the material of the wall into various things like isotopes of steel, isotopes of whatever you put in there. So you wind up with a somewhat radioactive machine, no matter what you do, pretty much. So when you run a Tokamak reactor, it's going to be highly radioactive when it's running. You can't go up and touch it. It's going to be contained in a big concrete shield. It's going to have a biological shield. It's not going to be something you can put in your car or not going to be something you can fix by going up and turning a wrench. You have to have remote maintenance. You have to have quite a lot of safety precautions. You have to be able to have materials inside which will stand up for 10, 20, 30 years of radiation-induced damage. Okay, and that's a problem I haven't mentioned. Radiation at this level, neutron radiation, will tend to damage things. So one technological improvement could be radiation-resistant materials, which exist at small scales, but which haven't been tested at big scales. And then, finally, physics surprises. Even though I said cold fusion didn't work, it's maybe not impossible that we can figure out a way to increase the cross-section somehow. Actually, people have thought of one way, which I won't even ask you to guess, but there is one way. If you polarize the nuclear spins, nuclei have magnetic moments, and if you happen to polarize them so that they're aligned, you can actually increase the cross-section for fusion by a factor of 1.5. There might be other surprises. There might be a way to increase the cross-section, and that would make things a lot easier. Okay, this is the last few graphs. So I wanted to summarize by giving you a very cautiously optimistic perspective. What we're doing here is trying to make a fusion reactor with magnetic confinement. We're making progress. I think in my lifetime, we've made a heck of a lot of progress. Most of the hard parts and most of the progress is understanding this instabilities of the plasma, the turbulence and the MHD instabilities, which limit the confinement and the pressure. That's most of the problems and most of the progress. I hope I convinced you that it's possible to make a fusion reactor. I certainly believe it's possible. And ignition is almost obtained. We can probably obtain ignition in ITER. The question is whether it's the right way to go. Should we do it now? Should we spend that $5 billion? Or should we wait and try to think of something a little better? We can certainly make the next step if we want to and get ignition. And once we get ignition, it's fairly easy then to make the plasma appropriate for a reactor. Then the issues are more technological. Those technological issues go into the reactor design, which I showed you one of. I didn't dwell on the technology problems. There are lots of technology problems, engineering problems, once you get the plasma you want. There's the biggest challenge. At the moment, I think the Tokamak reactor is too complicated, too expensive, rather impractical. It just seems unlikely to me, even though I worked on Tokamaks for almost 30 years. I don't think we can make a reactor out of what we know so far in Tokamak, at least not a good one. We can make one just like going to the moon, but will it be a practical proposition? I don't think so. We need innovations. We need better physics, better understanding, and better technology. Maybe the alternate concepts are the solution. A little bit of tweak in the design will make it possible. Maybe I'm wrong. Maybe just by pushing one step further, everything will get better. I don't know. But this is our cautiously optimistic conclusion to what in this lab has been 50 years of work. Okay, that's all. Okay. My voice is running out, as it usually does. 10 minutes to 12, we can talk about, you can ask me questions or go off to lunch. I guess if you want to ask questions privately, I'll stay for a while. Yeah? Morale. Yeah, I think you probably see two sides of that from my own presentation. I think a lot of us are still here. Okay, we believe in it, and some are much more gung-ho than I am. They think that it can be done and want to do it. Some are discouraged from all of the difficulties. I think the morale is sort of in between there somewhere. Half of us gung-ho, ready to go forward, and in some respects, that's the big picture. In the small picture, most of us really like what we're doing. I'm measuring turbulence. I really think that's fascinating, and I would do that even if it wasn't for a fusion reactor. I think it's interesting to understand the way these little bubbles are made and do the physics. So most of us in the global scheme of things divide into pessimists and optimists, but in practice, in the daily work we do, we're here because we like what we're doing. It's a great place to work, and so is other labs in fusion. It's just a fun thing. It's like a big family. And for that matter, it's an international family, which is really great. We have friends all over the world, and it's essentially the same work we're doing. Yeah. I think it's unlikely there'll be maybe a few percent chance there'll be a great conceptual breakthrough, but that's what makes them great. I mean, you can't predict them. I don't know. We have one Nobel Prize winner in the lab, actually, strangely enough, but he won his Nobel Prize for discovering, when a graduate student, pulsating neutron stars in astrophysics. I hope it's possible to make a breakthrough. Every once in a while, somebody thinks they made a breakthrough. That's why I'm cautious. 10 times out of 10 in the past, these breakthroughs were not what they were cracked up to be. In other words, a lot of good ideas come out constantly, and they get tested, and either they're wrong or other things turn out to defeat them. So incrementally, we make a little progress, year by year, a little progress, little progress. Most of our progress is either a little bit or accidental, actually. So a lot of the progress is just accidental, running the machine and seeing what happens. Some of it's conceptual, but great conceptual breakthrough, or I think what you're talking about is an idea rather than a machine. Maybe, I hope so. Maybe one of you will come up with something. But we're going to continue to work on the assumption we're not waiting for that. Yeah.
One of the previous slides, there was a sentence at the end about direct conversion.
It's hard. In a Tokamak toroidal magnetic system, you somehow have to separate the ions from the electrons. The conversion is basically decelerating the ions, separating the ions from the electrons, and electrostatically decelerating them. So the 20 kilovolts or whatever energy they have at the edge is converted to electricity that way. It's hard to separate the ions and electrons at the edge of a Tokamak. So it works better in linear machines. There's designs for direct conversion in linear machines where the leakage occurs out the ends, and you can put stuff at the ends where the plasma leaks into it, and then you separate the ions and electrons. Space is at a premium inside a Tokamak, and you can't really get the plasma out of the Tokamak. So basically, there are no good ways in a Tokamak. Ask Mike now if that works for other machines. Mike's a good speaker. You'll enjoy this afternoon. Anybody else? Yeah? Yeah? Right. It's like a horse race. You can bet on the favorite, but get a small payoff, and you can bet on a long shot, but you get big payoff. Okay, and that's to me a long shot. It's a 100 to 1 shot. It might work out better, and if so, it would be fantastically great. But I'm sort of risk averse. I'd rather work on the thing that is the best shot, although it's quite difficult and probably the payoff is not so great. So it's a balance between risk and benefit. In detail, I find it hard to analyze to multiply risk or divide risk by benefit and come up with a number. It's more a temperamental thing. I think Sam Cohen, who probably told you about that, he's a visionary. He wants to make a fusion reactor, but he doesn't want to mess with all these problems. He wants to solve them right at the beginning with a new concept. And I applaud it. I think it's great. And it has interesting physics, too, so it makes it fun. But no, it's not I think it's typically 30 years behind a Tokamak. Oh, you're looking at my summer vacation. I took my family to Switzerland. That's another advantage of being in the field. You get to go to meetings, nice places, and get to take your family. No, this is actually in vacation in Switzerland, you see. The Matterhorn. Paris and Switzerland, and the meeting was in Switzerland. No, it was summer. Well, I guess you could still go explain. No. That's Geneva. I could give you a travel log for the next 5 minutes. Okay, I think we're done. If you want to find me later, I'm around. Yeah.
Sure. The purpose of in the end, the purpose of the wall, if the magnetic model was truly effective, you really wouldn't need a wall in the Tokamak, right?
Maybe.
But it's only there because since it's not effective otherwise, that burning hot gas would leak out.
Well, eventually you have to have some wall to stop the neutrons.
Right. I mean, or just a blanket.
Or a blanket. Yeah, the blanket would effectively be the wall. And it has to be still inside the magnetic field for the plasma to be confined there. So the wall actually, the little barrier that's the vacuum vessel is relatively small and easy. It's there, but you'd have to have something there to make the blanket. So you can think of it as the surface of the blanket.
Made by the coils, right?
No, actually the coils are outside the blanket.
Right.
So it's the vacuum vessel, so going outward this way. Plasma, the vacuum vessel, the blanket, meter thick, and the coils, because the coils are sensitive to heating. You don't want to heat up these cryogenic coils, so you stop every single neutron.
That's amazing.
Okay?
Listen, let me ask you, what's so significant about, isn't the Tokamak emitting a lot of neutrons? What's so significant about ignition?
It's when you, it's the point, it's somewhat arbitrary, when you can stop heating it externally.
It'll be self-sustaining.
Self-sustaining, yeah.
Which will obviously make it a lot more efficient.
Yeah. When you get to
So-
that point, you can begin to make a reactor.
So what's the problem with ITER and it gets to ignition?
It should.
So if it does get to ignition, besides, the only thing left to having a practical fusion reactor is efficiencies and size
Yes,
and
yes, yes. And engineering difficulties.
But you're saying once it gets to ignition,
Yes.
you spend your $1 billion powering it up.
Mhm.
It'll continue indefinitely.
Well, you see, ignition is necessary but not sufficient. Once you get to ignition, it still be so expensive to get there that you never make it.